Hello everyone. We are going to talk today about how we modernize the process for text classification at Insee, French National Statistical Institutes. There is a link to the slides if you want. We are both data scientists at innovation team at Insee. I am Tayebjee Couralet, previously occupying different roles in IT team. And this is Milam Tayebjee, who will do the heavy lifting of the presentation. We'll talk about the MLOps pipeline we put in place for text classification, why we developed a new PyTorch package, and how. And for the context, basically, as a statistician, we like to classify things into a big nomenclature. For our use case here, we use a business registry, so the Siren for those who know it. We need to, given an activity description, we need to classify it into one of the nice label. One specificity of that nomenclature is that there is more than 700 class, and we have not many text to go with. Each activity description we need to classify is only one or two words. But what we have in our case are additional variables to classify with. We also have human annotators if we need it. For the training data, we use what we had from previous classification, either by a deterministic algorithm or a fastText algorithm we used since 2021. One constraint, a big constraint, is that we can do training on GPU, but we have to do inference on CPU. We don't have GPU in production where we will use the predictors. We also have to be vigilant on inference time, which are not batched. There is no batch. It's on an API. Mela.
So after this use case description, I will get deeper into the MLOps pipeline that we have currently at Insee, and where we are going to modernize it using PyTorch-based models. So this is the ideal MLOps pipeline, that theoretically ideal pipeline that comes from data to the ML model training and deployment, and then the operations, and then you're looping back into data. So ideally, every step of this pipeline is automated, and everything is smooth and goes without any problems in an automated way. So this is the ideal theoretical pipeline, and this is currently what we have. So you have two main blocks in our current, let's say, deployment system. We have the Siren production teams, which are based in Nantes. And so it's mainly developers that do not have any data science background in its sense. And we have the innovation team. So this is where Cedric and I are working. It's based in Paris. It's mainly data scientists. So less ops, but more ML. And so we are working on the Onyxia SSP Cloud Data Lab, which is open on the internet based on a Kubernetes cluster. And so here are all the different blocks, we can say, the different steps in the pipeline, from data storage to data versioning, data cleaning, model training, model storage, model serving, to monitoring dashboard. And so the blocks that are underlined in, surrounded in bold, we'll get deeper into that and we'll analyze it a bit more in the following slides. So we'll get deeper into the data cleaning process, into the model development, of course, which is the core of this presentation, the development of the torchFastText package. We'll also have a look at how we are using MLflow extensively in our pipeline. You can see that MLflow is at the core of everything here, from training to storage and versioning of the model. And we'll look also at the API serving, how we're using FastAPI to serve the model. And just to tell you more about how we're dealing with the production teams. So for now, and this is an area of improvement on our side, is that all the dashed line here are not automated. They should be in the ideal theoretical MLOps pipeline, but they are not currently. So what we do is that we train the model and we send it to the production teams along with the Docker image of the API. So then they can redeploy it in their secured offline CPU-bound environment. And from time to time, we do what we call an extraction of the Siren database, and they get back to us the data for a retraining of the model. So that's how it's done now, due to security constraints mainly. And this is an area of improvement to automate all of these dashed line here. So first, the first block that I underlined here, it's data cleaning. So this is a very critical step in our pipeline at the beginning. It's basically when the data comes back from the production teams, you store it, of course, but then you have to clean them because the data is coming from another ML model, which might not be reliable as we want. So we need to use expert rules to clean the data before training a new model. So basically, we're using very basic techniques such as regex or deterministic techniques. And it's always expert-guided rules. So we have at Insee some expert on the nomenclature that we want to classify in. And so here it's very, very basic, very deterministic. We have full control about this. But it's a critical step to have, at the end of the day, a model that is reliable and that respects the standards of the expert-based rules. Then we use a lot MLflow in our pipeline. MLflow is absolutely critical in our full pipeline, from model training to model, let's say, serving. So first, as a training monitor, as a data scientist, we track all the metrics on MLflow during training. So let's say the training loss, validation loss, accuracy, and so on. All the basic metrics are tracked during training thanks to MLflow. It's used as a model store and versioner. For those who know MLflow, it's very easy to first look at all the models that you have, to compare between them, and also to promote a model if you have decided to continue with that. So MLflow is used as a model store and versioner. And we also use the PyFunc object from MLflow to wrap the model. So we have your PyTorch model, that does a lot of things, prediction and so on, and it outputs a tensor, which is a float, basically. It's not really readable by a human. And what we do is that we use the MLflow wrapper to just serve everything from raw text. So you just put as an input the raw text, like, I don't know, the activity description, and it does the pre-processing of the text. It goes through the PyTorch model, and it converts the logits into something which is human readable in terms of label. So this is this wrapper that only takes raw input and outputs something which is human readable, is done also by a PyFunc object, and MLflow enables an easy service of a trained model. So models are packaged with all the metadata necessary to run inference. So basically, this is a wrapper that I described just before. You have all the pre-processing here that is handled. You go through your PyTorch model, and you also process the responses at the end of the day. And so this is not seen by the production teams. That is key. It's fully controlled by the data scientists. And it enables an easy service and easy deployment into production. To validate the model, which was also one of the bugs that was highlighted in bold, we have a custom metric that measures the trade-off between how much do you automatically code and how accurate you are on the automatically coded samples. And all the different points here have several thresholds, confidence thresholds. So basically, if you have a low confidence threshold, you code a lot, but you are making mistakes. And if you have a high confidence threshold, you code less automatically, but you have a higher accuracy. And then it's up to the production teams to choose the threshold that they want. So for instance, if they choose this threshold here, they will code automatically 80% of the samples, but they will have a lower accuracy than if they were coding less. And to get going with the MLOps pipeline, we're using FastAPI for API serving, which has many advantages for easy service, such as simplicity, standard query format. It's scalable and modular, and it's a simple design thanks, once again, to this MLflow wrapper. And we use Argo CD for continuous deployment. So this is a code chunk from the predict endpoint of the API, so it's really easy. You just have to call your model.predict, which comes from MLflow. Thanks to MLflow, we are able just to have a one-line API in a sense, and it's very easy for production teams to take the Docker image of that and to maintain it without knowing anything about what happens within the model. It's up to the data scientists to make that work before in pre-production, in a sense. This is a schema of how it's done. Basically, we have the API, which is related to the S3 storage, and the client interrogates directly the REST API to have the answer. And it's very easy this is the publicly deployed API that we have deployed on the SSP cloud, which is the Onyx instance at Insee. It's very easy for me to have predictions for a given activity description. I can even change here. So I'm basically interrogating my API here, and it's giving me the code, the prediction. So I can also output something which is a bit weird with accents. I don't care. It will be pre-processed by the API. There will be no bugs given the raw input of that. And to monitor, which is one critical step in the MLOps pipeline at the end of the pipeline, you have to monitor your model once it's deployed to detect distribution shift, to check if the model has a stable behavior, or to decide when to retrain a model. So it's absolutely key at the end of the pipeline to monitor how your model fares into production. So we cannot have accuracy in real time for several reasons. First, it's the security constraint. We cannot have a look at the model that is directly deployed in production in Nantes. And for the API, we also want to track it. So how do we do that? So the API in Nantes is logging its activity, and from time to time we fetch the data from the production environment to display on a dashboard to monitor in real time how the model fares. And it's also, this step here is often overlooked in several MLOps pipeline, but it's absolutely key to have an observability of the model. And so at the end of the day, this is what we have in a sense in production right now. You have your API that is interacting with the MLflow and the training data. It, in a sense, churns logs in the dashboard data here, and then a dashboard here is retrieving everything related to the dashboard to track the model in real time and regularly. And I will let Cedric describe a bit the torchFastText package.
Yes, so why did we develop a new package instead of just distributing a PyTorch model? There were several reasons. One, like said before, we use fastText in production to this use case, for this use case. But as you may know it, the fastText library was archived in 2024. And this caused problem in production context. We don't want to have one or crucial library to be archived. We want maintenance. So several strategies behind the idea to develop a package. One, we wanted to use the simplicity of the fastText architecture model to use it to deploy a PyTorch model in production. We hope that adapting a PyTorch model and pushing it to production will allow us in the future to publish more complex model in production. To develop our custom PyTorch model is also to be able to adapt and customize the architecture for specific needs. Like I said, we use a lot of additional variables from our data to predict. We have control over the maintenance for this package. And we can use all the PyTorch ecosystem to add features for our package, like explainability or calibration. In the future, we hope also to use maybe pre-trained model from Hugging Face, but that's when we will have GPUs in production, not today. The package provides a standard and flexible architecture for all coding needs, and it's adapted to us in particular. The architecture is really close to the one from the fastText paper, and it distributes the raw PyTorch model and the Lightning module. So it's not the torchFastText package is not necessary to run in production. Like Melam said, we don't use the torchFastText model for the inference. We use it for the training, and it makes the training easier. We also publish it in open source and to collaborate with all that have those needs. If you want to explain.
So, I will present quickly the main features of this package. So it's really easy to instantiate a raw PyTorch architecture using just the few parameters that you have, and these parameters are mirroring a bit what is done by Meta in their fastText package, the Python API. In a sense, we wanted to get very close to what is done in the original fastText package to ensure a smooth transition between the fastText that was in production and that is used by many users around Insee and other NSIs in Europe towards this PyTorch-based model. And so you can see here that the module here, it's a Lightning module, and you can see here if I print the module, it's for those who are accustomed to PyTorch. It's basically a raw PyTorch model with a Lightning module above it, and you just have to call module.train to launch a training. So the idea was really to mirror what was being done in the original fastText package for easy training and easy initialization of the model. Then we also have this famous n-gram tokenizer from fastText. So you have this object n-gram tokenizer from the package that enables you to tokenize any text. And the wrapper class here to launch training in like a few lines of code. You are able to train a PyTorch-based model. So the idea is to target people that are not used to PyTorch but want to have some text classification use cases are maybe accustomed to the original fastText package, and the idea is to ensure a smooth transition between all the pipelines that were in fastText into these PyTorch-based models. And so an additional feature such as explainability can, so we're using here captum, which is a library in Python to explain predictions from PyTorch-based model. And then you can see that you can measure how a word or a letter is influencing the prediction. Here you can see that the sentence is rénovation de bâtiments dont électricité, plomberie, serrurerie, menuiserie. This is an activity description, and you want to see which word has had more importance in the prediction at the end of the day, which is 4332A, the NACE code. And so you can see that it's menuiserie that is driving, masonry that is driving the prediction. So this is used in production, and it enables the managers of the Siren team to have more insight on what's happening in the model without knowing anything about PyTorch or data science or anything like that. And so for the perspectives that we have now for the future, on the MLOps part, you remember that we had a lot of dashed line, especially between innovation and production, and we really want to bridge that gap to have this eternal knot of the MLOps pipeline in a fully automated way. So we'll be working into that to have a full automation between especially the model qualification and the model deployment in production in Nantes, and the looping back with the data that comes back from the production teams into the innovation team, and to continue having a better observability of the model once in production to be able to retrain automatically when we detect a distribution shift. And then on the package, on the modelization part, we want to get going with this open sourcing and this text classification toolkit in a sense, and we want to get from torchFastText to torchText classifiers, a library which will distribute a lot of raw PyTorch-based text classification architectures and untrained, because indeed on a Hugging Face you have a lot of trained models. But these models, you don't have control over their architecture because they are often big birds or things like that you cannot run into your secured or CPU-bound environment. And what we want to do is to offer users the ability to have a full control of, on the PyTorch model that they want to design for their production environment, and especially to have a reduced size models that are not maybe not available on a Hugging Face. And also, if you want to train yourself your models on your specific data, it's something that we want to cater to. So we want to distribute all sort of architectures, including BERT, label detention with fastText, and so on. So at the end of the day, what we really want to do is to offer a toolkit to distribute any text classification architecture for easy training and easy deployment. With the custom parameterization, you can do a small BERT if you want, and small BERTs are not that available on Hugging Face. Hugging Face is done to distribute big models that are already trained, and to enable easy training and inference on GPU, CPU. And also, around the raw PyTorch-based models, we also want to offer additional features to train and use a custom tokenizer from Hugging Face, so the BPE tokenizer. For instance, all the tokenizers that are available on Hugging Face, we want to offer the ability to train really easily a new tokenizer on your specific data, to control uncertainty using tools such as conformal prediction, explainability, as we showed just before, or calibration, quantization of your model for more of a faster inference. Also push-pull from HF. So basically, if you have the same parameterization as a model on HF, using a raw PyTorch model, you should be also to retrieve the weights from Hugging Face if you want to. So the idea is that Torch text classifiers offer small models, but once you have parameterized it to be big enough, you can retrieve the weights on Hugging Face if they are available on another trained model on Hugging Face. So the idea is to have a connection with Hugging Face at the end of the day if your parameterization corresponds to any model that is already present on Hugging Face. And so yeah, the main target is for those who cannot directly use big models from Hugging Face and or want to train their own flexible and customly parameterized models. And so always fully open sourced. That's the philosophy of our public institution. Thank you for your attention. And if you want to look at our code, everything is available on GitHub at this QR code.
Thanks a lot. Any questions?
Thank you for a great talk. I have a question. Do you propose any, or make any comparison study with original fastText, for example, trained on Wiki or Common Crawl?
Sorry, can you repeat? It has been a bit.
Do you make any comparison study with original fastText trained on Wiki or Common Crawl, for example?
On Wiki or Common, no, we had our fastText in production on our data, and we of course compared it. So it's this plot here. So before changing the model in production, we of course have checked if the new it's there. You can see that on this curve, the torchFastText in blue is above the fastText in production right now. And we also checked to see, especially on the tokenizer part, to see if we had the same results at the end of the day. But we didn't have, but it's a good idea though. We'll try to have a sort of benchmark. So we did it on our data, but not on common data, such as the one you mentioned.
Yeah, two questions in one, in fact. Is the trained model already available? Because us, like social scientists, are doing this by hand usually, which is quite stupid, but all we have. And do you have the same thing for the PCS nomenclature, which is the profession of the workers?
Yes, so for those who know, maybe NACE is open data. So we will be able, especially if there's interest from researchers and so on, we will be able in the following months to publish to Hugging Face. We'll try to do that. That's with some caveat maybe from Cedric.
Yes, this is the goal. We want to publish it. We want to do it in the good way. That said, we don't want to just upload it and let it live or die for our model. We want to tie it to a data set. We want to version it. So it's not so easy to do it right now, but it's a goal.
Yeah, so that's for the NACE, and happy to feel free to write it to us if you have a specific needs. For the PCS, it's a bit more complicated because it's personal data. You have names, you have addresses, and so on. You have many sensitive data about persons in this data set, and it's very unlikely to have the model that will be outsourced. The code or everything is outsourced, of course, but the data and the model that is trained on this sensitive data will be very, very, very unlikely to be published.
Thank you for this impressive talk. Just a small question. What is the calendar of the roadmap, which is quite impressive for the next steps, especially for bigger models?
You said the timeline, basically, yeah? The idea is for 2026 to be able to have a lot of new features on this package, and it will also be dependent on how the users react and the needs from Insee data scientists and Insee statisticians. We are also interacting a lot with other European institutes, Spain, Norway, Italy, and so on. So it depends also on the use cases that everyone has, and also from the industry or researchers. But the idea, yes, is to really get going with this package and to have it very quickly.
Thank you for the presentation. So you mentioned that you want to invest in being able to train a BERT-style architecture in the future. Have you already compared the accuracy with maybe pre-trained BERT with the small model versus a larger transformer, either pre-trained or fine-tuned or even tuned from scratch on your data set? Does the extra size and cost of the bigger model justifies the additional complexity and cost?
So for the past few months, we were really focused on how to put a model into production. And so we were really focused on how to have these 200 milliseconds inference time for one sentence, which was on CPU. That's on CPU, which was undoable with big BERT models. So we haven't really investigated a lot into those big models. Now that we have validated the idea of having PyTorch model in production, and now that the first PyTorch model has been deployed and it's giving good results, we will be investing a lot into the scientific benchmark and comparison of all those options that you mentioned. It's not done right now, but the idea is really, and that's why we want to have all these models in the package. The idea is to have easy benchmarking of these models. But unfortunately, with a production-minded spirit, it's very unlikely since we don't have GPUs in production to deploy BERT-based big BERT models.
We can thank the speaker again and have a small break before the last talk of the afternoon. Thank you.